Okay, so today we're going to look at two more sections in Chapter 14. One of them is going to be Section 5, which we're going to talk about tangents to a sphere. And the other one's going to be Section 7, where we're going to talk about chord, secants, and tangents. And where last week we were looking at angle measures, this week we're going to be looking at lengths of line segments. So the first thing, just as a reminder what a point of tangency is, this is the tangent line right here, and the point of tangency is at one point where it touches the circle. Now with the problems that we're going to do today, we're going to assume that this is a sphere instead of just a circle. The one thing that's new today is we're going to talk about that there is this radius to this circle that's going to be perpendicular to the tangent line through the point of tangency. So I'm making a right angle right here. Now the reason I'm making a right angle right there is I want to be able to use the Pythagorean theorem to help me figure out what it is that we're looking for with this particular setup. So if you think about it, sometimes you go up on a tower or you go up on a tall building, and whenever you go up on that building, the further up you go, the farther away you're going to be able to see. So with what we're doing, we're going to be able to estimate the distance that you're going to be able to see if you go up on this tower or this building and you look out across towards the horizon. Now there's a couple of things that we're going to assume whenever we're doing this. We all know that the Earth is not a perfect sphere. The Earth is bumpy, and at some places the radius is more than the other. So what we're going to do is we're going to use an average radius. The other thing that we're going to assume is that there are no obstructions between where we are and where the Earth curves around. So in other words, where the horizon is. So there's a couple different assumptions that we're going to have to use so that we can use this particular idea for the problem that we're going to do today. So here we are with an example. I have this tower that's in Hong Kong. The whole tower is 1,211 feet tall. It has an observation deck right here that's 722 feet off the ground. And the question that we're going to try to answer is that on a clear day, so in other words, it's clear, there are no obstructions, how far should we be able to see from the top of this observation deck? So the first thing we're going to do is we're going to construct ourselves a diagram. This circle right here that I drew represents the Earth. I marked off the radius of the Earth, 3,960 miles. We're going to use again an approximate or an average because the radius of the Earth is different at different places around the Earth. So we're going to use 3,960 miles. Here we have our tower that's 722 feet tall. The next thing that I'm going to do so that I can solve this problem is I'm going to put in a line of tangency. Now here's my line of tangency. It touches the Earth right here at this one tangent point, and the tangent point is going to show the distance that we'll be able to see, because now the Earth curves down and around and our eyes don't see around a curve. So this is going to be how far we can actually see. So what we're going to be looking for is we're going to be looking for this distance between the top of the tower and this point of tangency. So right now I don't have a right triangle, so I'm going to add in a radius of the Earth so that I do have a right triangle. Now the first thing that you're going to notice right here is I have different units of measurement. Here I have miles and here I had feet. So the first thing I'm going to have to do is I'm going to have to switch my feet over to miles. And 1 mile equals 5,280 feet. Too many zeros. And that needs to be an equal sign. So 1 mile equals 5,280 feet. So what I did up here is I took the number of miles I had, or the number of feet I had, and divided it by how many feet were in a mile so that I could figure out what part of a mile it is. We've done things like this, like whenever we were trying to use this circle and we would take the measure of the angle that we had and we'd put it over 360 because we knew a whole circle was 360. Well, we know a whole mile is 5,280 feet. So if a whole mile is 5,280 feet, to figure out what part of a mile this is, I would just divide the two. And that's how I came up with my 137 thousandths. Now this is just an estimate. It's a number that goes on and on. I just rounded it to the nearest thousandths place. So now this length out here is 3,960.137 miles. And this, since my right angle is here, this is my hypotenuse. This is my radius that we talked about that's going to be perpendicular to my tangent line at my point of tangency. So now that I have these two sides set up, I have the hypotenuse, I have one of the legs, I can put it into the Pythagorean theorem, which I did right down here. So I put it into the Pythagorean theorem. I know this is a hypotenuse, so it goes over here. I know this is one of the legs, so it goes here. And I had to figure out what the other leg was. So whenever I went through the process of, I had to square both of these numbers, and then I had to subtract them, and then I had to square root, and I came up with it's going to be approximately 33 miles. So from on top of this tower right here, I can see about 33 miles out to the horizon. You're going to have a couple of problems on your assignment to do today that involves this. One of them will be miles and the other one will be in kilometers. Remember that if you're talking about meters, there's 1,000 meters in a kilometer. And then there's 5,280 feet in 1 mile. Okay, so that you're going to need these conversions. It will give you what you need for the radius of the Earth. Okay, so now let's go on to the second section that we're going to look at today. This second section is going to be looking at chord, secant, and tangent lengths when they intersect. Now the other one, they didn't intersect. We were just looking at finding some distances on a sphere. So these are going to be on a two-dimensional circle. We're going to have basically two different ideas. Are they going to intersect inside the circle, or are they going to intersect outside the circle? There's one situation, of course, when they intersect inside the circle, it would look like this. To intersect inside the circle, it would have to be two chords. Two secants could intersect inside the circle, but we would be looking at the part inside the circle. Here we have two secants that intersect outside the circle. Here we have a secant and a tangent that intersect outside the circle. And here we have two tangents that intersect outside the circle. Now each time we're going to be going out here to this intersection point. So we're always going to be starting from the intersection point. So let's first look at the inside the circle one. So here we have a circle. I have two chords. Okay, the two chords have this intersection point that I'm going to call P. Okay, so any two chords that intersect at this circle, there's something called the power of P. The power of P in this circle. And any two chords that intersect here are going to have the same proportionality. So, in other words, if I multiply this section of the chord by this section of the chord, it's going to equal the same thing as this section of the chord multiplied by this section of the chord. And we call this the power of the circle at P. Now, if we had a different intersection point, then the power would be different. But the power of the circle at P is going to be what we multiply together, and the power of this circle at P is going to be 12. So the power of the circle, and that should say at P. So the power of the circle at P is the product of those two segments. And basically that's one side of the equation. So the power of this circle at P is 12. 4 times 3 is 12. I left out the word at again. So there we go. So the power of the circle at P is 12. So it makes it pretty easy to set it up and figure out. So I know that for both chords, the power would be the same. So I'm going to say that if I multiply PA by PB, I've got to get the same thing as if I multiply PC by PD. So then I set it up. I just called this one X. So this power is 12. So 4 times 3 is 12. And on this side, I need some number that if I multiply it by 2, I'm also going to get 12. So I just worked it out, and I found out that this section up here would be 6. Oops, can't see that. I need to change. There we go. So this part of the circle up here would be 6 because 4 times 3 is 12 and 2 times 6 is 12. So that's going to allow me to figure out what that length up here is. So this is when they intersect inside the circle. I just multiply intersection point to outside point by intersection to outside, and then I do the same thing here. So I always go back to the intersection point before I start doing the measuring. Okay, let me go back for a second. Notice here that if I would add these two together, this chord is 7 units long and this chord is 8 units long. I'm not saying that the chords are the same length. What I'm saying is the power of P would make the chords multiply together to give you the same power number. It's not the lengths have to be the same, but the power number has to be the same. So let's go out here and look at this one. This one's a little bit different. This one I have two secants that are intersecting outside of the circle. So if I look at this, I'm looking at my two secants, and I notice that they intersect out here. Now remember, whenever I did the other one, I always had to go back to the secant. So what I want to look at right here is I always have to go back to the intersection point. So if I'm looking at this one, SF multiplied by SA. So again, I have to go all the way back to the intersection point and then out to the end point. That's going to equal the same thing as SR multiplied by SE. So again, notice how I did this. I went all the way back out to the intersection point. So SF is right there. So that's my first piece. And then my second piece, I go all the way back to the intersection point and then, oops, out to the other end point. Sorry about that. That was a little messy. And then here I have SR. And then I go all the way back to the intersection point to get SE. So if you look at these, I have two pieces. I have this piece right here, which is a small piece, and then I have this long piece right here. Don't make a mistake and just use the 9. So if I'm looking at this, okay, so if I go back here and I look at this, it's going to be 3 times 12. SF is 3, SA is 12. So if I'm multiplying SF and SA, SF is 3, SA is 12. And then if I come over here and look at this one, SR is X and SE is X plus 5. So you notice this one is going to give you a quadratic whenever you multiply it out. So the first thing I'm going to do, oh, and by the way, the power of this circle at S is going to be 36. So I need both sides to wind up equaling 36. So here I have this one, 36, and I have my problem, my expression over here, where I need to multiply them. I multiply it, and I have x squared and 5x. Okay, so I have x squared plus 5x minus 36, because remember, to solve a quadratic, I have to move everything to one side of the equals. So I subtracted 36 from each side. So now I need to solve this quadratic equation, and I have a lot of choices here. I can use the quadratic formula. I could use graphing if I wanted to. I could complete the square. I'm going to use factoring. Okay, so I'm going to look at numbers that will multiply together to give me negative 36. And I want numbers that will add together to give me positive 5. So if I think about this, and by the way, remember I got the numbers from here. Negative 36 is what I want to multiply to. 5 is what I want to add to. I know that 4 times 9 is 36. And I also know that if I take 9 and I add negative 4 to it, I'm going to wind up with 5. So I've got negative 4 plus 9 is 5. Negative 4 times 9 is negative 36. So those are my two solutions, or my two factors, x plus 9 and x minus 4. Now, if I go through and solve this, this is going to give me x is negative 9. This is going to give me x is 4. We know that we're never going to have a distance that's negative. So I'm not going to use the negative 9 because it doesn't make sense for that to be negative 9. I'm going to use the 4. So that's going to tell me that SR is 4 and that SE is 4 plus 5, which is 9. So now if I go back and I look at the beginning where we were talking about the power being 36, 3 times 12 is 36. And 4 times 9 is 36. So I had to make it so that both of these were going to equal 36. And that's how I did that, is I had to set it up and solve a quadratic. Okay, so here is one where we have two tangents. Well, actually, we don't have two tangents. Sorry, we have a tangent and a secant. Okay, so here's my tangent and here's my secant. So the first thing I'm going to do is I'm going to figure out what the power is. So if I look at this, I know that to find the power, I'm going to be looking at GH, and I want to multiply GH by GF. Oops. Okay, so GH by GF, so that's going to be 3. GH is 3. And GF is 3 plus 6, which is 9. So the power of this circle at G is going to be 27. Now, up here, I only have one segment that I can look at. So since I only have one segment that I can look at, I'm going to give it a variable. I'm going to call it X. And in this case, I'm going to have to use the X twice. So where I did this one is GH and GF. This one I'm going to do GE times GE. So I'm going to do GE times, and I'm going to use it again. I'm going to use GE again. So if I come over here, GE times GE, I'm just going to call it GE squared. Instead of using GE over here, I think I'm going to use X. Okay, so that, oops. So this is going to be X squared. Okay, so let's, okay, so X squared equals 3 times 9. So then I just sort of work it out. Okay, so all I'd have to do would be square root, and you can't see the square root symbol there, but what I would need to do is square root 27. So GE equals the square root of 27. So this one, I'm going to have to use an estimate. It's about 5 and 196 thousandths. Notice that on these I've been rounding to the nearest thousandth. So you should probably try rounding to the nearest thousandths whenever you do this. Okay, so this is where I have a tangent and a secant. The next one is actually the easiest one. Here it is. This is the one I want. When I have two tangents. So if I look and I have two tangents, the points of tangency to the circle are the same length, same distance to the intersection. So this one makes it a lot easier, because with this one, I just take WM and it equals WD. So that makes this one pretty easy to solve. I take 2x minus 10 equals 56, and then I go through and I solve it, and I find out that x is 33, because I know that these two have to be the same distance from each other. So those are the three different types of problems that we are going to have to work on. So let's go ahead and try some and see how we do. Okay, so here are 4 problems for you to go ahead and try. Try them out and then go to the next slide, or pause the video and do them, and then whenever you're done, go ahead and look at the answers on that will come next. Okay, so here are the answers that I have. For the first one, I got approximately 46.7 miles. The first thing I did was change the 1,450 feet into miles, so I divided 1,450 by 5,280 and got about 275 thousandths, and then I substituted it into the Pythagorean theorem, and I got approximately, I think it was 46.66 something, so I just rounded it to 46 7/10 miles. For the other 3, on number 1, the power was 108, and then I used the power to figure out what the other piece of the chord was. On number 2, the power was 592, and then I used that to figure out what the other measurement was. This one I got an approximate answer, again, 14.889 about. And then the last one, I found that the power of A is 64. And then I worked it out and found out that the piece there that was missing is 7 8/10. Okay, so this week's assignment, I've attached it below. I've also created a Join My Quiz, because one thing I'd been noticing whenever you were turning in your work, some of you were checking your answers and some of you weren't checking your answers, because there's been a few times I've seen answers that were just totally off topic, that you had done it a totally different way, and that kind of told me, hey, you're doing the work, but you're not checking to see if you've done the work correctly. So to get full credit for this particular assignment, you are going to have to go to the Join My Quiz, and you're going to have to complete the quiz, which will be the exact same problems that you're going to see on the worksheet, but at least then I'll be able to see that yes, you have checked your answers. So be sure to use your real name in the quizzes so that I can give you credit. Please don't go in as a guest. Use your name so that you will know how to, so that I will know that you went in and checked your answers. Have a good week. Next week we're going to be talking about surface area. Take care.